when we were talking about Fourier-Bessel series, at one point we encountered a certain integral that was called the normalization integral, because it involved taking a scalar product of a function with itself. And that integral had the following form. So it's the product of x, which was the weighting function of our scalar product, jn squared kx dx. So this is the integral that we're going to play around with in this video, first in its general form over here, and then we will integrate from 0 to 1 and make sure that k is a 0 of that Bessel function of order n. So let's get started step by step, and I suggest the first step is to use a substitution t is equal to k of x, so that we can more easily use our well-known formulas. And then let's also do integration by parts. So let's split up the integral into a part which contains the Bessel functions and a part which doesn't contain the Bessel functions, and then make a judgment call which one of those you will call u and which one you will call dv, and see if you can perform that integration by parts. First up, the coordinate change. So x is equal to t over k. So if we move from x to t, we will pick up a factor 1 over k here. But the same is true if we move from dx to dk. We will again pick up another factor. So that's going to be 1 over k squared, the integral of t jn squared t dt. Now, in terms of integration by parts, it makes sense to choose d dt as dv, because we know what v will be. It will just be the integral of t dt. So this is going to give us t squared over 2. So that's an easy choice. It would have been much more difficult to choose that one here. So let's then have jn squared as u. Okay, so if we have that, then let's do the integration by parts. So we have 1 over k squared, and then here between square brackets we should have uv. So u jn squared t, and then v is t squared over 2, minus the integral of v du. Let's not forget about the k squared, minus k squared, the integral of v du. So v is again t squared over 2. And then taking the derivative of u will give us 2 jn prime dt. Okay. Right, so yeah, cleaning this up a little bit, that gives us t squared over 2 k squared jn prime of t minus 1 over k squared, the integral t squared jn prime dt. Okay, so that's the first step. So now we need to focus our attention on this rather nasty looking integral. But what are we going to do? Well, if you look at this integral, you might recognize this particular guy here, t squared minus jn, because that is a term that actually figures in Bessel's differential equation. So try to calculate this term from Bessel's differential equation, multiply that by that guy, which we still have left, and then if we're lucky, then the end result might be something that we can write as a total differential, and then we can immediately solve this integral. So let's see if this works out. Calculate this term multiplied by that and try to write it as a total differential. So if we have Bessel's differential equation, that was t squared, so now expressed in terms of t. So t squared jn double prime plus t jn prime. And then we had so n squared. So then we had t squared minus n squared jn equal to 0. But what we're going to do is, of course, factor out our t squared n squared and bring that to the other side. So basically we have now that we have minus t squared jn that's equal to t squared jn double prime plus t jn prime minus n squared jn. Okay, good. That's the first step, but remember this is not our integrand because we need to multiply here by jn prime. So let's do that next. Minus t squared jn prime is equal to t squared jn double prime jn prime plus t jn prime squared minus n squared jn prime. And here comes the magic, or the flash of divine inspiration if you want. You will realize, or you might not realize, it's not that straightforward, that this thing over here is in fact the total differential of t squared jn prime squared minus n squared jn squared. And if you weren't able to make that step by yourself, don't worry, you can always go the other way around and use this as a given and verify that if you take the derivative, you end up here. So let's do that. Let's just verify. So we have 1/2, and then we have, sorry, that should obviously be d dt here. So we have 2t jn prime squared plus t squared 2jn prime jn double prime minus n squared 2jn prime. So now we need to verify that this thing is equal to that thing. Well, all of these factors too, they will cancel, so that's good news. Here we have t jn prime squared. That's what we have over here. This term is the same. And then also that term we find over there. So indeed, we verified that this is the total differential over here. Good. So now that we have this thing, we can finally write down what our integral is. Our integral is equal to that first part, which we already calculated thanks to integration by parts. That's going to be t squared divided by 2k squared, jn squared of t. And then we have a new thing here. Let's not forget the 1 over k squared plus 1 over k squared. The minus sign that we had here is taken care of already by that minus sign over there. So we have 1 over k squared, and then we just have this thing over here. So we have 1 over 2, and then we just copy this thing here. So t squared jn prime of t squared minus n squared jn squared t. Okay, that's good news. That basically means that the case is closed, but already we can do some more simplifications and clean stuff up. So what I suggest we do now is we go back to t is equal to kx. So make that substitution, clean stuff up, and then we can take the step of integrating this between 0 and 1 and actually calculating our normalization integral. Okay, well, obviously there should be an integration constant here, but let's not worry about that. So the integral here, so remember the definition of the integral that we were interested in was the integral x jn squared kx dx. So this was again the definition. And now we look back at this thing here and we make the substitution back to kx. So here we have t over k, so t over k, that's just x. So this is going to be x squared over 2. Let's move to here. So this is going to be x squared over 2. Jn of t is equal to kx squared. Okay. Then for the next thing we have 1/2. Then t squared over k squared is again going to be x squared, jn prime squared of kx. And then finally we have minus 1/2 n squared over k squared, jn squared kx. Okay, simplifying this a little bit more because we realize that these two guys, of course, have common factors. Speaking of common factors, we also have x squared over 2 here and here, but not here. So let's quickly rectify that by having an extra x squared in the numerator and the denominator. And then we can factor out x squared over 2. Let's look at this term first. X squared over 2, we have jn prime squared kx. Okay. Then we have terms involving jn squared of kx. So the first term just has a coefficient of 1. And then we have a coefficient of minus, and then we have here n squared over k squared x squared jn squared kx plus the integration constant, which I keep forgetting, but which is not terribly important. Okay, right, so we've calculated the integral, we've cleaned stuff up, that's good news. Let's now take the final important step, and that is transforming this into the actual normalization integral, where we go from 0 to 1, and where we replace k with an actual 0 of the Bessel function of order n. And then hopefully all our hard work will be rewarded and we get a very simple end result. So let's keep our fingers crossed for that. Okay, we're interested in the integral from 0 to 1 x jn squared psi I x dx. And we know that this is the primitive of that integral, so we need to evaluate that between the bounds 1 and 0. Let's first do 1. So this is equal to, so we have here x equal to 1, that's 1/2. Then we have jn prime squared of psi I, so x is equal to 1 and k is equal to psi I. And then we have plus 1 minus n squared divided by psi I squared, x is equal to 1, and then we have jn squared psi I. Okay, that's the upper bound. Then for the lower bound, x is equal to 0, so you might be tempted to think that the whole thing vanishes. That's an easy mistake to make, but let's not forget that there's also an x squared over here. So this thing is the only term that's left. The minus here becomes a plus, so that becomes plus n squared over k squared. And then we have jn squared, and if x is equal to 0, this is jn squared of 0. That looks easy enough, but perhaps we can simplify this thing even more. Let's focus on the second term here. Don't forget, psi I is not just any scaling factor, it's actually a 0 of this Bessel function. And thanks to that, we're very happy to get rid of this term here, so that thing cancels. What happens with Bessel functions at the origin? Well, we know that Bessel functions at the origin are always 0, except for the case where n is equal to 0. But if n is equal to 0, that means that this guy is equal to 0. So regardless of the value of n, we're again very happy to get rid of the final term as well. So now it becomes very simple. We just have 1/2 jn prime squared of psi I. And that looks simple enough, but we can have a final cosmetic transformation by getting rid of the derivative and expressing that in terms of a Bessel function of 1 order higher, as we've done before. So this is the recurrence relationship here that we're going to make use of. And if we replace x by psi I, since psi I is 0 of the Bessel function, this thing cancels. If we take the square, as we should do here, then the minus signs will disappear. So finally, we can also write this as j n plus 1 squared xi I divided by 2. And that's a very simple looking end result of a, let's admit it, scary and complicated integral.